liquid in the bottom of the glass. The surface continually moves up to the high surface tension region, dragging liquid up with it. It will keep pumping like this indefinitely, but since the liquid that is pumped up has no place to go, it accumulates at the top of the film, accumulates so much that it forms into drops that roll down, drops that are called wine tears. Notice that the drops have difficulty getting back into the deep liquid. Perhaps you can figure out why, remembering that they have less alcohol in them than the bulk liquid. Electrical charges, as well as kinds of molecules at a surface, affect the magnitude of surface tension. Electrical charges usually concentrate at surfaces where their repulsive forces on each other subtract from the surface tension. Mercury in dilute sulfuric acid with a bit of potassium dichromate added will form a chemical battery if another metal, an iron nail, is brought in as a second electrode. When the two metals touch, the battery is short-circuited and the charge density on the mercury surface is reduced. The mercury drop pulls up due to increased surface tension. With just the right position for the nail, the mercury will set itself into oscillation, repeatedly short-circuiting the electrical charges that build up when the mercury is not touching the nail. Mercury in nitric rather than sulfuric acid, again with potassium dichromate added, provides this example of surface tension variation. The electrical and chemical effects at the surface lead to surface motions that cause the mercury to swim toward the potassium dichromate crystals. The third way to vary surface tension is to vary the temperature of the surface. Increasing the temperature always lowers surface tension of a liquid. It becomes easier to pull molecules up into the surface. Heating this metal plate warms the liquid above, reducing the surface tension there. The warmer surface is pulled away, dragging some liquid with it. The opposite happens with an ice cube. Liquid above becomes cold, has a higher surface tension, so nearby liquid is pulled into the cold regions, causing humps rather than depressions. Now let's imagine what should happen to a gas bubble immersed in a liquid when the liquid has a temperature gradient. When, for example, the liquid is hot there and cold here. The cold side of the bubble will have a higher surface tension than the warm side. It will therefore pull surface around from the warm side. Surface will be generated here, flow around the bubble, and disappear at the cold end. This movement of surface with the viscous drag upon the boundary fluid will pick up a sheath of liquid and jet it off the back end. By jetting liquid this way, the bubble propels itself that way. It will swim up the temperature gradient, always moving to the hot region. Here we have a bubble. It moves to any hot region. If you wonder about the thermodynamics of this self-propelling bubble, wherever surface is created, heat is absorbed, and wherever surface is destroyed, heat is given off. Therefore, this bubble is absorbing heat at its hot end and rejecting heat at its cold end. It is a self-propelling heat engine. Here is a related experiment involving bubbles that can easily be done in the kitchen. Place an ice cube on a metal surface. It will turn around and around in its pool of melted water and perhaps stop and then move back and forth. This motion is caused by bubbles that attach themselves to the metal under the ice. Any motion of the ice causes a temperature difference over the bubble, and each bubble, through surface tension variation, acts to push the ice above it in the way that it was already going. If you try this, use homemade ice cubes, the kind that have bubbles in them. Swimming bubbles can also occur on a heated wire in a mixture such as acetone and water. At low rates of heating, bubbles of acetone and water vapor are generated at nucleation sites on the wire, but instead of rising off the wire, they will swim along the wire in a stately parade. Notice the jets of hot liquid that the bubbles project backwards. A moving bubble surface drags hot liquid backwards and jets it away from the cold end. The velocity of those jets suggests that the bubble surface is moving quite fast, about 1,000 bubble diameters a second. That is part of the explanation of why they move along the wire. Once they start moving, the wire is colder where they have been and hotter where they are going, so they just keep going to where it is hotter. An interface is more than just a geometric boundary. It exerts forces, forces which are sometimes important in large-scale systems, such as in space where gravity is weak. But more typically, surface forces are important in small-scale phenomena where the surface-to-volume ratio is high, as in most of the examples we've been looking at. Using the idea of surface forces, these phenomena can be understood.